Okay, another type of characteristic is something called high specific heat. So the specific heat is the amount of heat that must be absorbed or expended to change the temperature of a substance 1 gram for 1 degree Celsius. So that's kind of a long explanation of basically how much energy do you have to pump into something to make it actually change temperature. All right? Water, you have to pump in a lot of energy to get a temperature change. Okay, so maybe just write that down to kind of sum this up. A lot of energy for a change in temperature. And you guys should know this from experience of living in Minnesota. Okay, in order to warm up our lakes in the spring, it takes a long time, right? It takes a series of many warm days before the lake water feels warm enough to swim in or whatever you want to do in the lake. Okay, water takes a lot of energy. It can absorb a lot of energy before it actually changes heat or changes temperature. So examples of other ways that we see this, night versus day warming and cooling is the first example. So even though it gets really cool at night or very warm during the day, it doesn't change the temperature of our lakes drastically. Right? It takes a series of very cool days or very warm days to change the temperature of the water. And that's a good thing for the things that are living in that water, because if that water could change temperature really quickly and drastically, that would be hard on those fish and other creatures that are living in the water to deal with that temperature change. We also see this in the difference between coastal and inland countries. Countries that are close to the coast or close to water have more moderate climates. For example, England is basically at the same latitude as Minnesota, but they don't get nearly as cold as we do because they are closer to the ocean, which kind of calms down their colder temperatures, right? It keeps it warmer there. Also, if you're an organism with a lot of water content in you, again, something that lives in the water, for example, or a plant is another example of organism with a lot of water content, it would be bad if your water warmed up and cooled down really easily, right? You could freeze really easily or get too warm really easily. So the ability of that water to be kind of moderate also protects the organisms that have a lot of water in them. So again, all very important to living organisms. Another characteristic is the high heat of vaporization of water. Again, kind of a long drawn-out explanation here. It's the amount of energy required to change 1 gram of liquid water into a gas. And in other words, again, it takes a lot of energy to turn water into a vapor or into a gas, okay, to make water evaporate. Again, this is really important so that we can make sure that the water isn't changing into a gas really easily. That would be bad for a lot of living organisms if their liquid water turned into gas, at a low temperature. The reason for this is because of those hydrogen bonds again. Okay, it always comes back to this idea of the polar molecule and the hydrogen bonds. All right, when you apply heat energy, it has to break the hydrogen bonds. And in order to do that, it takes a lot of energy. It's also important to something that some organisms do, including us, called evaporative cooling, which means that when we sweat, we're actually cooling our bodies because the evaporation of that sweat causes that cooling. Okay, so the ability of water to evaporate, turn into a gas, can help cool organisms like us down. All right, another important factor about water is it's called a universal solvent. Remember, solvent is something that can dissolve something else, and by universal we mean it dissolves a lot of stuff. And that's important, that water has the ability to dissolve a lot of things. It is a versatile solvent, which means, again, it can dissolve a lot of different things. Very versatile because of that polarity of the water molecules. And this little picture here is kind of trying to show that. If we've got our little water molecules, these little Mickey Mouse ear looking things, remember they have positive and negative parts, that's that polarity again. They will surround and break up molecules that have charges. So we've got a block of salt here, which has positively charged sodium ions in it and negatively charged chlorine ions. Okay, the water is going to direct its positively charged hydrogens toward the negatively charged chlorine, and it's going to direct its negatively charged oxygen toward the positively charged sodium, which breaks up that salt. Okay, so the actual act of the positives and negatives of water interacting with the positives and negatives of salt makes the salt dissolve. And that's important for a lot of reasons. One of which is that we carry a lot of dissolved substances in our blood. So it's important that we have the ability of water in our blood to do that. This is getting into that a little bit more. As I just said, blood is mostly water, and because of that, it can transport all sorts of dissolved stuff, from nutrients to gases to wastes. All of that can be dissolved in our blood and transported around our body. This is a good time to bring up two new vocabulary words too, hydrophilic and hydrophobic, which we touched on in biology in 10th grade as well. A hydrophilic molecule is typically charged or polar, and because of that, because it has charges, it's attracted to water. The opposite of that is a nonpolar molecule we call a hydrophobic molecule that's repelled by water. And you can think about what these molecules are. Things that don't mix well with water are usually oily substances, for example. They don't have charges, and so they don't respond to the polar parts of the water molecule. They don't bind with them. And of course, then they don't dissolve in water either. Okay, moving on. Another important characteristic of water is that solid water, which we know is ice, is less dense than liquid water. So in other words, ice will float on top of liquid water. The ice is less dense than the water. In other words, the molecules are spread out to their maximum distance. And this little diagram down here at the bottom shows that. Okay, we've got an ice cube on top. If we look at the molecules, we can see there's a lot more space among those molecules. And notice the little dotted hydrogen bonds again. So the hydrogen bonds are still holding it together, but there's more space between them. Over here, we have the water itself, and what those molecules look like, a little more squished together. So they have the same mass, but the ice has a larger volume because the molecules are spread out more. Again, the floating ice is important to living organisms. This prevents lakes from freezing completely. The top layer of the ice will freeze. The ice will float on top, creating kind of like an insulation barrier on the top of the lake, allowing the water below to stay unfrozen during the winter, so different organisms can winter over in the lake and not die from freezing.